Welcome to day 32 of our STL course. Today we are diving into custom comparators and functors in C++. These powerful tools allow us to control how data is ordered and processed in STL containers. By customizing your comparators, you will be able to define exactly how sorting, searching, and even prioritization are performed, giving us full flexibility when working with STL containers like set, map, and priority queue. Let's unlock the power of custom logic in our programs. Let's go over the learning objectives for today's lesson. By the end of this session, you will be able to understand what custom comparators are and why they are essential for specialized data sorting and searching. Learn how to define custom comparator logic using lambda functions and functors. Apply these comparators in STL containers and algorithms to achieve custom ordering. Finally, we will cover best practices to avoid common pitfalls when using custom comparators in your code. Let's get started. A custom comparator is simply a function or object that defines how two elements in a container should be compared. By default, STL containers like set and map use the less than operator to compare elements. However, when you need a different comparison logic, whether it's sorting in descending order, comparing by a specific attribute of an object, or creating a custom priority, you can provide your own comparator. Custom comparators are essential for tailoring the behavior of STL containers and algorithms to our needs. So why would you want to use a custom comparator? Well, consider this. You might have a list of people and you want to sort them by age, not by name. Or perhaps you want to sort numerical values based on their last digit instead of their actual value. Without custom comparators, achieving these would be challenging. Custom comparators allow us to define our own sorting rules, which is especially useful when working with associative containers like set, map, and priority queue. We can also integrate them into searching algorithms to control how comparisons are made. There are three main ways to define custom comparators in C++. Function pointers, the traditional approach where you create a function to compare two elements. This is a simple and clear method. Lambda functions, a modern and concise method where we define a comparator in place. It's great for small one-off logic. Functors, a function object that overloads the operator so we can call it just like a function. Functors are reusable, maintainable, and ideal for more complex comparison logic that needs state or customization. Each approach has its own strengths. We will explore these in more detail today, so we will be able to choose the right one for our needs. Let's start with the function pointer approach. Here we define a simple function called test that compares two integers and returns true if the first one is greater. This function is then passed as a comparator to the sort algorithm to sort a vector in descending order. While function pointers are a tried and true method, they can be a bit verbose and less flexible compared to other two methods, but they are great for simple one-time uses. Now let's look at lambda functions. Lambdas are quick inline functions and they allow us to define custom comparison logic without needing a separate function. In this example, we use a lambda to sort the vector based on the last digit of each number. The lambda expression is concise and works perfectly when you need a small, localized piece of comparison logic. This is a great choice when you don't want to clutter your code base with additional function names or when the logic is short-lived. Next, we have functors, which are objects that overload the function call operator. In this example, we define a compare by age functor that compares two person objects by their age. We then use this functor in a set, ensuring the elements are ordered by age. Functors are particularly useful when the comparison logic is more complex or needs to be reused multiple times. Unlike lambdas, functors can also maintain state, making them more flexible for complex use cases. Here's a great example of a lambda comparator with a priority queue. In this case, we are sorting pairs of integers where we prioritize the second element of the pair. By passing a lambda to the priority queue, we can customize the heap's behavior. This allows us to create a custom main heap where the elements are ordered according to a non-trivial comparison logic. This technique is particularly useful for scheduling tasks where tasks are prioritized based on their urgency and deadline. Which STL containers rely on custom comparators, primarily the associative containers, set and multiset. These containers use comparators to determine the order of elements, map and multimap. The keys in these containers are sorted based on a comparator. Priority queue. This container manages elements in a heap, and custom comparators can change the heap's ordering. On top of containers, many STL algorithms also use comparators. For example, sort, binary search, lower bound, and equal range. All rely on comparators when they are provided. Custom comparators enable fine-tuned control over these algorithms' behavior. While custom comparators are extremely useful, there are some common pitfalls to be aware of. Our comparator must enforce strict weak ordering. This means that if A is less than B is true, then B is less than A must always be false. If this isn't the case, the behavior of containers and algorithms can be unpredictable. Avoid capturing variables in lambdas when used as comparators in containers. This is because containers like set or map may store a copy of the comparator, which could lead to unexpected behavior. Const correctness is essential. Ensure that functors are marked as const if they don't modify state. This allows them to be used correctly in containers that require const correctness. To wrap things up, there are some best practices. Use lambdas when your comparison logic is simple, short-lived, and does not need to be reused. Use functors for more complex or reusable comparison logic. Functors can also hold state, making them ideal for maintaining additional data during comparisons. Always ensure that your comparator is const correct if it does not modify any state. This is especially important when using functors with STL containers. Test your comparators thoroughly. It's easy to overlook edge cases, so always ensure that your comparators work correctly in all scenarios. Let's put our new knowledge to the test with some practice tasks. Sort a vector of pairs by their second element in descending order. Create a book struct and sort a set of books by publication year, then by title. Implement a custom main heap using priority queue to manage tasks based on priority and deadline. Now for your mini lab assignment, build a leaderboard system. Use a set or map with a custom comparator to rank players. Rank them first by score and then alphabetically by name. Implement functionality to insert and remove players and retrieve the top 5 players in order. Make sure to rank the scores in descending order. Before we finish, let's do a quick recap. Can you write custom comparators using lambdas and functors? Do you understand when and why to use function pointers, lambdas, and functors? Can you apply custom comparators to STL containers like set, map, and priority queue? Are you aware of the common pitfalls and best practices for comparators? If you can confidently answer yes to these questions, you are ready to tackle more complex STL problems with custom comparators. Thanks for joining today's lesson. Now that you understand custom comparators and functors, you can take full control over how data is ordered and processed in STL. If you have any questions, feel free to reach out. I will see you in the next class.